This is our third and final part to Introduction to Limits. We will now find limits algebraically, which basically means we don't have tables and we don't have graphs. We have to just use algebra. In order to use algebra, you have to just understand the properties of limits. The first property is a very basic one. It seems very simple. It seems confusing. It's so simple. Let the limit of c equals c. What we're saying here is all we have is a number. We don't have any x's in it. So if you look at our example here, think of it this way. Remember the limit of f of x as x approaches a is the basic form. So if we have a negative 6 in there, that means f of x equals negative 6. Well, remember, f of x is just y. So what we have here is we have a horizontal line, which is y equals negative 6. And it doesn't matter what x is. X can be approaching 3, as in this case, or negative 3, or positive infinity, or negative infinity. No matter where you are on the horizontal line, y will always be negative 6. Therefore, the limit equals negative 6. Every y value is negative 6. Now the rest of the problems that we do algebraically are all based on this statement that if you're taking the limit of f of x, you're just going to plug a into f of x and get f of a. And you can add, subtract, multiply, divide, raise to a power, take a root, before or after you take the limit, but as long as you have a real number, you are just substituting to find f of a. So these first two are very simple. In order to find the limit as x approaches 3, we plug a 3 in for x, and we get 9 minus 4 is 5, over 3 minus 2 is 1, and there's our answer. Our limit is 5. For this next one, we have a square root in it, but we can do that just by plugging in x equals 9. So we have square root of 9 plus 10 is 13, and in the denominator, 9 minus 10 is negative 1, so we have negative 13 as our answer, and that's it. Here's our first example of one thing we can do when we plug in and we get 0 over 0. If you get 0 over 0, that tells you there is some way that can be simplified, and we have 3 methods that you can try to simplify. So here we have limit of x approaching 1, and so when we plug in, we get 1 squared minus 1 over 1 cubed minus 1, which is 1 minus 1 over 1 minus 1, which is 0 over 0. So that tells us that we can simplify this. You'll see they seem almost magical the way they work out. So we'll take this, hopefully you're seeing, when you see the top of this expression, you're seeing right away, we know x squared minus 1 is a difference of squares. And so we know that is x plus 1, x minus 1. And you may have forgotten, but x cubed minus 1 is a difference of cubes. So we're remembering that c is x minus 1, and if you're forgetting at this point, you go into Google and you put in difference of cubes and get your formula out. But remember, it's opposite signs, so you have the first one squared. That's a minus, so this is a plus. Then you multiply the x and the 1, and you get an x. And then you, the last one is always positive, and you square the 1, you get a 1. Okay, so now we can see what happens here. We can cancel out the x minus 1s. And then we are ready to plug in, because the part that was 0 is the x minus 1. 1 minus 1 is 0. The rest of it isn't going to be a 0. So now we can plug in, and we'll get, we'll plug in the 1 to the top. We get 1 plus 1 over 1 squared. I'm just showing more steps. If you can do it in your head, that's great. And then we end up with 2/3. And if you were to graph this expression, you would see that as x approaches 1, it is 0.6666 repeated, which is 2/3. Okay, in our second example, we find we have division by 0, but we need to make sure that the numerator is 0 as well. So let's see if it is. Square root of 16 plus 0 minus 4 over 0. Okay, so the top of it is going to be 4 minus 4, which is 0 over 0. So 0 over 0 tells you, take courage, I can do this, I can do something to simplify it. Now obviously you can't factor this. You should be thinking multiply by conjugate. When you see, you're going to use, remember the formula is a plus b times a minus b equals a squared minus b squared. And you have no clue why this is going to work, but when you see an a minus b or an a plus b, it doesn't matter if it's in the numerator or the denominator, give it a try, see what happens. So let's get a different color here. Okay, so we're going to give it a try. We're going to, okay, I rewrote that so that I have more room to show here, and we are now going to multiply, let me change in color here. We're going to multiply the top and the bottom by the conjugate, which means we're going to leave the square root the way it was, and this was a minus 4, so we're going to put a plus 4. And then in the bottom, we're going to write the same thing again. Now here's where I have advice for you. Just leave the bottom the way it is. Don't multiply out the bottom. Just do the conjugate in the top. So you will have the square root of 16 plus x, the quantity, squared, that's your a squared, minus your b squared, which is 4 squared. And then the bottom is going to stay exactly the way it was. Just copy it exactly the way it is. Now you'll see what happens when you do this. When you square the square root and the square cancel out, and that becomes the 16 plus x minus 4 squared is 16. And I'm going to show all these cancellations here. The 16 minus the 16 is 0. So you just end up with positive x on the top and x on the bottom. So that can now be canceled out. And what's left on the top is just going to be a 1. So now you're ready to plug in the 0, because you don't have division by 0. That x is gone from the denominator. So you'll just plug in the 0, and you'll have 1 over square root of 16 plus 0 plus 4, which equals square root of 16 is 4, 1 over 4 plus 4 is 1/8, and then you're done. Our third example, when f of a is 0 over 0, is a complex fraction. And you can see what's happening here. We're going to plug in a 0. We get 1/4 minus 1/4 over 0. So that's a 0 over 0. So we need to simplify this complex fraction. So I've rewritten the fraction with the bottom fraction, making that into x over 1. And I'm going to show the method in which we combine the numerator into one fraction and then multiply by the reciprocal of the denominator. I believe that's easiest in this case because there are two different denominators, and you can just leave the denominator x over 1 and flip it as to become 1 over x later. So let's do this method. We're going to multiply the first fraction by 4 over 4 and the second fraction by x plus 4 over x plus 4, giving us a common denominator of the large numerator. So the top numerator just becomes 4 minus the quantity x plus 4, and do not multiply out the bottom denominator again. That's kind of a theme here. And then I just already wrote times 1 over x as we're working on the first fraction. So here, after we distribute the negative and it becomes negative x minus 4, you can see what's going to cancel out here. It's going to be very convenient, just like the last one. 4 minus 4 is 0. And the x's are going to cancel out. I'll rewrite that to make that clearer. Okay, I rewrote that, so you just have a negative x on the top times a 1, and you still have the times x on the bottom, so those x's are going to cross out. And now that all you're left with is the negative 1 on the top and the 4 times x plus 4 on the bottom, and we are now ready to plug in, so we have negative 1 on the top over 4 times 0 plus 4, which equals negative 1/16. Our last topic is finding the limit of a piecewise function, which sounds very scary, but this is actually simpler than what we just did. Now, if you remember a piecewise function, we have two parts. We have f of x is x plus 6 when x is less than 1, and we have x plus 9 when x is greater than or equal to 1. Now you could graph these, but you really don't need that to find the limits. So we're going to just plug in to find our limits. Now when we're finding the limit as x approaches 1 from the left, remember we want the x's that are less than 1, therefore we need to use the x plus 6 equation. That's where x is less than 1. So we just plug the 1 into that top equation, and we get 1 plus 6, which equals 7. Then, when we're finding the limit as x approaches 1 from the right, we want the x's that are greater than 1, so we will now use the x plus 9 equation and plug in 1 to that equation. So we get 1 plus 9, which equals 10. And therefore, the limit as x approaches 1 does not exist. And the reason is simply because the left-hand and right-hand limits are not equal. This last example shows the difference between a whole and a vertical asymptote. If you recall, when we studied vertical asymptotes, we said that they would occur when you have a simplified fraction with division by 0. But when you have a whole, remember, wholes have, if you look on this graph here, wholes do have limits. You can approach the same number from the left and the right when you have a whole. So let's see what happens in this problem. In this piecewise function, this fraction will be the one that we use when x is everything except negative 3 and 3. Negative 3 is where we have our whole. 3 is where we have our vertical asymptote. So you're really going to be using this fraction for both the left and the right. So in order to find the limit as x approaches negative 3 from the left, we're going to take the limit of that top expression. Now when we plug in negative 3 here, we have negative 3 plus 3 on the top, which is 0, and on the bottom, negative 3 squared is 9. 9 minus 9 is 0. So what we really have here is a 0 over 0. So we're going to have to do something to simplify this, and when we see x squared and minus 9, you should be thinking right away that factors into x plus 3, x minus 3. So when I separate into x plus 3, x minus 3, then you will see that the x plus 3's will cancel out. That'll remain a 1 on the top because there's nothing left in the numerator. So now when we substitute negative 3, we're going to have 1 over negative 3 minus 3, which is negative 1/6. So the limit as x approaches negative 3 from the left is negative 1/6. Now because that very same fraction is used from the left and the right, because we're just skipping x does not equal negative 3 or 3, but everything else is what that fraction is used for. Therefore, from the right is going to be that exact same process. You don't have to rewrite it. You know that's all the same process. So the answer to part C as x approaches negative 3 is negative 1/6. And you can see that sort of makes sense if you look on the graph. It looks like the hole is just a little bit below the x-axis, so that negative 1/6 makes sense. So that's going to be where the x approaches negative 3, you actually do have a limit. Now if we look at the limit as x approaches positive 3 from the left and the right, we will get, when we plug in, we get 6 over 0. Now when you get a non-zero over 0, that will be a vertical asymptote. So in that case, you need to test to the left and right, as we did in the tables, to see if it's negative or positive. You may remember that this one, when we simplified it, was 1 over x minus 3. That should ring a bell. We had negative infinity from the left, positive infinity from the right. Therefore, the limit did not exist. So that's the difference between a vertical asymptote and a hole. Now you have learned 3 ways to find limits, numerically with a table, graphs, or algebra.